Okay, so I want to start by going over the example we went over last time, both for review and to fix that typo I made that confused us during class. So recall test.py, this file. Used by something else. Yeah, this file, test.py. So it's x equals 1, y equals 2, z equals x plus y, print z. And recall the disassembly when we run the disassembler to look at what the bytecode is. I'm going to open up another window. When we look at the bytecode, we say python -m dis test.py. If you run this, you should see the following. So just for a quick review, hopefully everybody sees this exact thing. If not, you should look over at your neighbors. Just for a quick review, each one corresponds to a line here. So notice how line 1 here has these two bytecodes, line 2 has these bytecodes, line 3 has these, and line 4 has those. That makes sense? So there's a set of bytecodes for each line. These are the instruction names and optional arguments. So these opcodes all have arguments. This binary add has no argument because, as was mentioned last time, it implicitly takes the top two things off the stack, does an add, and pushes the results on the stack. And you can see all of this at work if you look at the Python documentation. So if you look at the documentation, if you look at Python this is the disassembly module. If you look at that, you press on Google, and if you actually let's look at binary add as the bytecode. So there's a reference for all the bytecodes. Binary add, it says this implements TOS equals TOS1 plus TOS. So this basically just means the top of the stack is set equal to the top of the stack plus the thing on the next to the stack. So it basically means pop the first two things off the stack and put the one back on. It might actually, depending on the bytecode itself, it might actually optimize it and just clobber the thing on the top of the stack. So it might not actually do two pops and a push. It might just do one pop and just override that thing. But conceptually, that's what that bytecode does. All these other bytecodes have roughly semantic meanings that you can look up on the documentation. Again, I don't expect you to memorize any of these. It's just they're all just documented here. So going back to our terminal, we have these bytecodes, and then the last line just returns something. So the mystery we got into last time was how big the set of bytecodes is. So each one of these has an offset. So this is a byte offset. This is at byte 0, byte 3, byte 6, byte 9, byte 12, 15, 18, 19. Notice how each of these have 3 bytes, right? Each bytecode has roughly 3 bytes. And it's usually 1 byte for the bytecode itself, and then usually 1 byte or so for the argument, and maybe there's an extra byte for something. There's probably some format. Sometimes they might take 2 arguments or so forth. But notice how this one, binary add, starts from 18, goes to 19. It's only 1 byte, right? Because there's no argument, so all I need is 1 byte to say binary add. It's some value bytes. So this goes all the way down to 30. So return value has no argument, so I'm assuming it's 1 byte. So this whole stream of things should be 31 bytes. And the mystery we got into last time was when we disassembled the bytecode, it wasn't 31 bytes. It was actually a lot smaller. It was like 10 or 11. So we actually resolved this by I actually compiled the wrong thing. So I'm going to show you what the right answer is. So, so we're going to go back here, and we're going to clear the screen. I'm just going to type Python. And now I'm going to say C code equals compile. Now I actually am going to open the file .read and then test.py exec. So the mistake I made last time was that I actually just passed in test.py as a string into the first argument, right? Where the actual compile function expects you to just a string of all of the source code. So what this function does is this calls open to open the file, and then calls read to read the whole thing in the string. So now this essentially is the string of the entire file's contents. What I did before was I actually just literally passed in a string called test.py. So it actually was trying to compile a program as a string test.py and not this whole thing. That make sense? So now that it actually compiles this whole thing, everything is a lot more sensible. So when I type C, it's a code object. So c.co _code is the code for it. And notice that this is a string. It's actually pretty long now. So if I put len for length, I just hit enter, it's 31. All right, this matches with our intuition that this piece of bytecode in some encoded format is exactly 31 bytes, and that's exactly what the disassembler tells us. So you won't ever have to read this manually, but it's just a sanity check to see what the assembly tells you. So as another quick sanity check, if I actually did the mistake like I did yesterday, and I just compiled test.py, can anyone tell me what is a program that's just this string? What does that program look like?
Trying to access some number of test object.
Good.
It's going to be.
So that's a lot shorter, right? So let's actually look at the assembly. So it's actually 11 bytes big. So this program is actually a program with one line. You have an object test, and then you do a dot on it, and you're looking up a py member on it. Obviously, it won't run because there's no test object, but that doesn't mean it doesn't compile, right? Like programs can compile all the time but not run. So let's actually look at that. Just to, again, to show there's no magic going on here. So let's actually make a program called, I'm going to make a file called like bad.py. I actually did. Look at that. Actually made that. So bad.py is a string, just test.py. So if I try to compile it or disassemble it, look at this. So what this is you have to really squint at it, but this is one line. Right? This program has exactly one line, so all these bytecodes are for line 1. This has a load name instruction that loads the name test. So it kind of loads whatever this test refers to, which is nothing because it'll break when it's running. Then it does a load attr of the py attribute. Load attr is this the dot operator. So it's just an opcode for loading an attribute or field or member of an object. And then it pops the top of the stack, and then it loads a constant none, and then it returns. So remember, the end of all modules or functions, if you don't say return something, it would load a none object and then return it. So why do you think, as an extra question, why do you think there is, they have an idea, why is there a extra pop instruction there? So if there wasn't a pop instruction, after we exit, what would be on the stack? So it would just leave something on the stack, right? And this is the only reason I think this is there is because we never actually use it or consume it. So we actually just loaded something. This put one element on the value stack. We just want to take it off and clean it up, and then we're going to put the constant on and return it, which pops it off. It's just a way of cleaning up after yourself so that the value stack doesn't leave some garbage.
Wouldn't it cause some exception if the stack is empty and then you're still going to pop it and there's nothing to pop? Is that okay?
Oh, so you mean if I actually run this code?
No. Like whenever the stack is empty and then you pop it, does Python have any way to check?
You mean, will this code throw an exception sometime?
Yeah. Even if we have test dot, no, we don't have that.
Yeah, I think it will generate different codes. If I say x equals that, let's actually see what happens. So I'm assuming that it only does that because there's no other things. Now it doesn't do the pop. So notice if I actually do x equals test.py, it actually loaded it. So this is exactly the same program except we assigned to x. It actually loaded it here. So this part does the load, and now this one stores this one stores it in x, that actually popped it off the stack implicitly, stored in X, and now we clean up ourselves. And I think the only reason why this thing is there is because we didn't assign it to anything. So in no possible execution would. So your exception question is interesting because we won't worry about exceptions right now. The exception question is interesting because when you actually have if something happens, like there's an exception, then the exception handler will clean up the stack for you at runtime. So, and there's a lot of the interpreter code is exception handling, which is we won't go into because I don't think it's very interesting. It's just really messy.
Yeah.
All right, so basically, if you execute this code, this is a good point. So if you execute this code, right here it'll blow up, right? Because there is no test. So right here there'll be an exception, and it will try to clean up after itself. Make sense?
Yeah.
Okay, so that was from last time, and then again we're gonna just go into the interpreter itself just to have a high-level overview of what happens when this kind of straight line no function code is run. So we're going to open up a text editor. So remember ceval.c, our friend here, and I want you all to verify that the line is exactly the same as I have, because I don't want to make sure I didn't edit the file. So it's 693, right? Is that the right line? For eval frame ex, this main function? Is 693 everybody's line? Okay. So make sure we're not off by one. Okay, 693. Okay, so again, the lightning overview of all this is, recall that the first part of this function just declares a lot of local variables for our convenience. So this function, what it does is that it executes one frame. So we're going to go into what a frame object is this hour. It executes one frame and it returns an object or a pointer to an object. So this is what happens when the Python interpreter executes one frame, or equivalently one function. And then at the end of the function, it has to return the value to whoever called this function. So it turns out when we're executing test.py, there is no function because we just wrote code by itself, but it executes as though it was one function. That's why there's like a return none at the end. It just executes what's called a module as just a block of code. There's a lot of local variables here that it stores for state here. And let me scroll down here. Okay, so then there's some timing stuff, which we don't need to worry about. There's a bunch of macros for accessing the stack. So these are macros. The predict thing you'll have to go through in your assignment. These macros are just convenience things for accessing the value stack, looking at the top one, popping it, pushing it, and so forth. You can ignore the LL trace. You can assume that's not on. Just again, assume all these profiling macros are not on, and just use the basic versions. There's get local, fast locals, and this is the start of the code, right? So again, tracing, all the stuff you can ignore when you're doing your assignments, tracing stuff. These assign local variables just as convenience of it takes, the first thing it takes actually is the code object out of the frame, which we'll see in a bit, and then it takes the names and the constants. It needs to know what code to execute, basically, because given a frame object, it needs to grab the code of the function, and it needs to know what to do with that code. And it's going down, and this is the main loop, right? This is the main infinite loop that's going to go, and in each iteration of the loop, it's going to go, again, more profiling code. It's going to grab the next opcode. 1080 is next op. Next op is just a macro for grabbing the next opcode out of the code stream. Argument is it tries to grab the argument. So if has arg opcode, so there's some macro that defines whether an opcode has an argument. So I'm just going to go here, this has arg. So if you go to opcode.h, opcode.h again is just the definition of all the opcodes. All opcodes are just numbers. Has arg is defined down here. It just says the opcode is greater than equal to have argument. have argument is just a, so you can look all this up here, it's just a number, just 90. So basically I said everything below 90 has an argument, everything above 90 has no argument. So, you know, if you're above 90, you have an argument, and if you have an argument, we're going to grab the argument out so that you know not only the opcode, but the argument to call it with. And then there's a giant switch statement in 1112. So basically through the loop, every time through the loop, with some exceptions, there's a bunch of, there's a condition for every opcode. I mean, it's just exhaustive. Pop is a good example. So here's a really simple opcode, right? We saw this. Pop underscore top, all it does is it pops the value off the stack, assigns it to a temporary, and then decrements the reference with temporary. So PyDecref means we need to decrease the reference count because nobody, you know, we want to just erase it for now. And again, in Python, if there's no other references to the object, it'll disappear. So the idea is, let's say I have an object. Let's say I have, you know, so the value stack is here. Let's say I have an object, you know, 1 here, an object 2, and object 3. Right now there is, you know, because these things are on the stack, there is, you could say there's a reference to each of them, right? The value stack keeps a reference to all of them in order. You can imagine as an array or linked list. Then somebody else might be pointing to 1. So maybe somewhere else x is referring to this 1, and somewhere else y is also referring to this 1. So should have drawn this backwards. Sorry. Let's say x and y are both referring to 3. So when someone says, let's say someone executes the instruction pop top here, what happens is it pops off the stack, which means it just manipulates the stack to just take this 3 off the stack. So then, as far as we know, it's not on the stack, but then it actually has to decrease the reference count. So the reference count here was 3 things were referring to it, and now it needs to record that only 2 things are referring to it. Because remember, C is not it's not a garbage collector language. Just because you take a reference off of something, the object does not know that someone doesn't have a reference to it. It's actually Python, the interpreter needs to implement its own garbage collector because C has no garbage collection. So there's 2 references to it, and then now let's say somebody else, you know, if somebody else erases the pointer from X to it for some reason, then we need to actually call the decref so there's only one thing pointing to this object. And if later on someone erases the Y reference to it, we need to decrement this to 0. And then when this is set to 0, Python's garbage collector knows to actually reclaim this space and collect it as garbage. So Python uses what's called a reference counting garbage collector. That's why you'll see a lot of these references to PyDecref, or also there's PyIncref, which increases the reference. So let me give you a PyIncref example. PyIncref example is, let's try store. Store name. So store name, there's a decref here, right? That's weird. If store name isn't the best example. Is there store fast? Sorry, I'm just going off on a slight tangent here. Set locals. Okay, well, I can't find it at the moment. But basically, the way the opcode work is just this loop all around. And the main data structure is this value stack, which is just a single stack of objects and things. And all the opcodes, all the bytecodes do is operate on that value stack. So recall Python m dis.py. Dis.py. Everything just operates on this value stack. So whenever you see bytecode, you don't even need to worry about the source code anymore, right? Like that Python interpreter, all it knows is how to execute all this stuff. It doesn't even care what source code it came from. So you can imagine compiling it to bytecode and then just giving someone the bytecode. So actually, when you run Python, behind the scenes, when you say python.test.py, it prints 3, right? Because Z is 3. Behind the scenes, if you look at this directory, Ah, it actually doesn't create it. It's weird, because usually it creates a PYC file, which is the compiled bytecode file. I don't know why it doesn't create it this time. It's too small or something. But usually what happens is it actually creates a pre-compiled bytecode file so that you don't have to compile every time. It's not a giant deal because the parsing and compiling stuff doesn't take a long time, but it saves a little time. Okay, so now let's actually go to the main event of the day. It's let's go to the main event of the day, which is getting out of VI. Wow, this is terrible. The Sigwin VI is terrible because it doesn't allow you to customize anything. You have to type in because. Okay.
Yeah, back to Emacs.
Yeah, I know. That's how it does. Okay, so now let's actually modify our test.py. You can write a new one or modify it. So, okay, so now the code for today's example is going to be a little longer. So it's x equals 10, def foo of x, tab y equals x times 2, return bar of y, def bar of x, y equals x divided by 2, return y, z equals foo of x. I suppose I can print z too, but it doesn't matter. Okay, so you can take some time to type that in. I think I typed it in right. You don't have to put the last print z line, but I just want to double check to see if it works. Okay, it's 10. Good. Oops. Okay, so people have that typed in, more or less? Okay, so we're actually going to step through the code from the source level first just to see what happens. And fortunately, I have this tool that I've made to do this. So we're going to step through this in a tool that I've built. Is this not copy? Wow, okay. There has to be a way to copy because, should I just open it?
I think you just highlighted it.
The highlight is copy?
Copies.
All right, let's test this hypothesis. So I have this tool that I built, I've been maintaining for a while, that actually, it's called Python Tutor, you can just follow online. Good work. It actually allows you to type in code and actually visualize it. So this is the exact code we have, and we're actually just gonna step through the execution. So, oh, it works better on Chrome. Fine. Okay, so people can see the code here. What this will do is this will trace through the execution of all of the code one step at a time. So there's 12 steps. Let me zoom in a little bit. You can see. Let's get it really big here. Okay, so what this says is we're right before the first line. So this is just like a visual debugger. So it's just like you can step through the code debugger. So you know, this sort of project would be really good for the class project analysis tool. Okay, so we're gonna step forward. When we step forward, the global frame, the global scope has one thing, and it's x goes to 10. That make sense? After we execute the first line, there's a variable x that's been created that maps to 10, and that's not executing this line. Make sense? Okay, we're gonna keep on stepping. So, line 2. Actually, what do people think this execution line, what should it do?
Load another frame.
Load another frame, okay, other ideas? So this def_foo is a function definition in Python. So when it...
Will it compile the code and put it in a code object?
Good. It will compile the code and put it in a code object. Good. So that's... I think what it does is technically it all compiles it before, but it actually, what this line does is actually... I knew my drawing... The Internet Explorer is off a little bit, sorry. Wow, okay, Internet Explorer is totally off. I'm going to do this in Chrome. So, bear with me for a second. So the great news is I can actually just copy the link. This is going to work better in Chrome. So IE on the tablet has some weird sizing issues. So pretend like we're starting again. Fortunately, there's this handy feature that you can just copy a link. And we're back. All right. So what we just did here was we stepped through, right? So the first step defined an X object that points to 10. The second step actually defines a foo as a name and points it to a function object with the code to foo. So actually, technically, it compiled everything beforehand, but executing that line actually bound the name foo to the actual function. And the function contains the code object, contains the code. The function also contains some other stuff, but it contains, that will be next class. But the function fundamentally contains the code. So when we so notice how going through this line 3, it doesn't execute foo, it just defines it, right? It just creates a name that you can use later. Same thing with bar. This actually creates a bar name that maps to the function. Good so far? So we haven't called any functions yet, we just defined them. Now this line is where we actually call the function, z equals foo of x. So we actually first start by stepping into foo. So if you notice, we jump into here, and now this is when we create another frame. So there's a global frame, the stack goes downward, right? And then there's this frame here, it's highlighted. This is the frame for foo. This is just standard calling function, so you can see this in any language. X points to 10, because this is the X that's a local variable, right? Now there's two X's, right? There's an X here, and there's also a global X out there. I purposely made it that way to confuse people. There's two X's. There's one local, there's one global. The next line, when it executes, it just steps in the function. Now y equals x times 2. Y is 20. Makes sense? Because it actually looked up the local x, because this x refers to the local x, if there is one. If there isn't one, it'll look in the global. And then it just multiplied by 2 and it gets 20. So y equals 20. Makes sense? Now we're going to call another function, return bar y. So now we're going to call a function, bar, and we're going to step in another frame. So now we have a function, we have the global, we have foo, and we have bar. Make sense? Now bar has an x, and that's 20. And it's because we called it with this y, right? This is this. This is this. Does that make sense?
I
So,
have a question.
yes.
So is the stack here the value stack?
No, this is the function frame stack. So it's not the value stack.
It's not the value stack.
Not the value stack at all. Because a value stack only exists in the VM. This is a source level view of Python, right? So when you're looking at a source level view, there is no value stack. It's just a bunch of frames and functions. You can imagine putting a value stack in here, but that'll require finer grained tracing. Be a great project idea. I can tell you how to do that, what challenges are involved. But this is a tool for kind of a source level view. So this stack is it's called the frame stack, I guess, or the function stack.
I'm a little confused though. So you said the value stack is in the runtime.
Yeah.
And this is the source view. So this is even before the run.
No, this is actually running. So this tool actually runs the code. This code is actually running.
Yeah, I understand that, but I mean I don't quite get how come there is another, like the source stack here.
There's another stack.
Right. Where is it?
Where is it? Okay.
It's not the value stack, but
we'll get to it in a sec. So today's lesson is that.
Oh.
So there is another stack. There's not only a value stack. There is in the interpreter there is this stack too.
Okay, I see.
Right. So there's a value stack which you don't see in this picture, and there's the function frame stack, which is what we're using.
Okay. Yeah, got it.
Make sense?
Yes, makes sense.
Okay. So we're here now. Recall we're here, and we're gonna step again. Now y equals x divided by 2. Y is 10. Which x is the y using now? It needs to look up an x. So which one is that? Good. This one, right?
Yeah.
So there's this x, there's this x, or there's this x, right? So it's this one, because this is the local one. It will actually never act as that x, because it's it will either look in the local or actually it will look in the global if it's not there. It will actually never look in this x. But okay, so that's where we are, and then we're going to return it. So remember, returning it just sets a return value. So I just identify this as a special return value variable. It returns y, pops back up, so that whole stack disappears because we return out a function. Now we return the value of bar y, which was 10, and then that disappears, and now z goes to 10, and that's our answer. Does that make sense? So if you're reasonably familiar with Python or any other Python-like language like C, you should be able to eyeball this code and see that z is 10, right? I made this example straightforward enough that you can eyeball it. So it's a very convoluted way of basically saying what foo does is that it just takes a number. Conceptually, if you actually look at what foo does, it's always happens, sorry. What foo does is that it takes a number, it multiplies it by 2, and then it returns bar of it. Bar takes a number, divides it by 2, and returns it. So foo actually doesn't do anything, right? It actually, as long as you have an integer, it actually will be exact, because multiplying by 2 and dividing by 2 are inverses, because you won't get a round off error. If you have a floating point, you might get a round off thing. And if you divide first and then multiply, you get a round off thing. So this should give you an identity function. So it should do exactly nothing. Okay, questions on what this function does from the source code level? If you're confused about this, then there's no point in moving on. So this should be fairly clear. Okay, so now let's actually look at the bytecode. So we're going to spend the rest of the 40 minutes or so looking at bytecode. So we're going to go back to our terminal, and we're going to do the disassembly again on it. So python -m dis test.py. The font's a little bigger, so that's not terrible. Okay, if we stare at this disassembly, some things might look straightforward, some things might not. So line 1 is here, straightforward. Load constant of 10, store name x. That's load 10, store in x. Does that make sense? That's straightforward. Line 3, line 1, 2, 3. Line 3 is this one. I'm just going to mark it so it's clear. Line 7 is this one. Line 11 is this one. Make sense? 3 and 7 do the same thing. Load constant of a code object, blah, 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 blah. Make function, which creates a function of it, and then store in foo. Load constant of a code object, make function, store in bar. So those two lines respectively creates a function object out of the code that was precompiled. So the code is actually precompiled. So, I mean, you have no way of knowing that, but all of the code is precompiled beforehand. So when Python compiles this module, it will compile all the code for this, and then it'll look inside all the functions and compile all of their code and make them into code objects. So they're ready to go. But the kind of dynamic thing about Python, this is one of the dynamic things, is that the function is not bound until runtime. The code is compiled, but the function is not bound until runtime, until this line gets executed. So one way you can imagine this, well, actually, we will really get into this next time, but does anyone have ideas for why there's a you already compiled the code. Why is there a separate step, some separate magical bytecode to make it into a function and then assign to something? This is kind of hard to answer now, but do people have ideas on that?
Because you can hot swap somehow. You can kind of later on switch to something that just you can change it and
Yeah, you can change it dynamically. Yeah, I mean, it kind of goes into the dynamic nature that I think you're kind of hitting on the deeper point here, where conceptually speaking, the code object is really the code of this function. Forget the name, right? There's no name. Forget the name for now. The code is kind of like this, right? This piece of code without a name is a function with one argument called x, a line of code here, and a line of code here. This piece of code has a thing, a thing, a thing. These code objects are immutable, right? This looks like it's, when you write this, like it's just a glob of code. But at runtime, it actually, so this code object is good. So this code object is this blob right here, and this code object is this blob without the name. Now at runtime, it actually binds it to this name. So one of your points is you can bind it to a different name, or you could hot swap it out. But the thing we'll see next time is that the difference between a code object and a function object is that the function contains a code object inside, but it also contains something else. For those of you who study like programming languages or compilers, what other stuff does it contain? This is kind of a subtle question. Does the term closure mean stuff to people? Have you all heard of the term closures? Okay, so kind of vaguely. So a function object is actually a closure. So again, you don't need to know this right now. We'll go next time. A closure is a piece of code and an environment point that points to the defining environment. So the reason why this code object is run at runtime, this function is made at runtime, is that it needs to bind to the right environment. So the function object, the difference between a function object and a code object is that the function contains code and it contains a pointer to its environment. In this case, the environment is this. The environment is the fact that there is a global with x equals 10. Because if it didn't actually know that, if it actually didn't know that x equals 10 and you try to access a variable x here, it doesn't know to look in the globals. So the code object itself doesn't know how to look in the globals. And like your point is, the same code object can be reused as functions in different scopes. So don't worry about that too much, but that's what the conceptual difference between a code and function object is. And we'll have a whole lecture on this. So we covered this line, covered this line. This final line, what it does is this. It loads foo, loads x, calls the function, stores, and this you can ignore, right? Load, return 0. So let's just focus on this. Load foo means it just loads the name foo, just tries to find it. It so happens that foo is bound to the function, which is good. Loads the name x, and then calls a call function opcode. The call function opcode does what you'd expect. It actually calls this function and does the magic. And then at the very end, after the function is done, it will store the result of the function return value in z. And that's the z equals thing here. So that line makes sense?
In mine?
Yeah. Yes.
In mine,
Uh-huh.
it's not doing
Okay,
this,
let's see.
but it's doing it.
Let's see. Oh, so you have an indentation problem. So you have to actually unindent that, the
Yes.
last line. Yeah, so indentation actually matters. So save.
Alright.
Right, so this is a thing for people new to Python. That's actually a good point. You can save as the same document, yeah. And then go to execute it. Good, it has the same line, right? Okay, good. So this is good you brought that up. So Python indentation actually matters. So if you actually did this and you indented it, this would mean that this call is inside of the bar function. So which means that the code will not. So actually, let's look at it. This is good. Good example. Then there's no call, right? There's no call to function. Yes?
How do you do the binding? How does the interpreter find the code object based on the name of the object?
Good, that's a good question. So how does it find the, wait, hold on. Let me go back to the original example. I'm gonna try to understand your question, but you mean on this, how does it do binding, or here, where does it do binding?
At runtime, how do you find the you know, at runtime, you need to bind the code object to the function call.
Uh-huh.
How do you fund the code?
Okay, so I guess in this example, are you caring about this line or this line?
The second part.
11, line 11, this one, right? Okay, so you're saying at runtime, how does interpreter do that?
Right.
Right.
How does the interpreter find the code to execute?
Good, good. So it finds a code to execute because at runtime, if you notice, all this does, this opcode does, is it loads the name foo. It just so happens that foo is bound in the environment to a function object. And this function object is bound to has a code object inside. So it actually looks up, load name actually looks up the string foo and then gives me this object back.
Do you look up from a table?
Yeah, it's a dictionary or a hash table, yeah. So it's a table, just like how, actually this is a good question. So load name x goes to an object called 10, right? So when I load name x, it actually gives me an object 10. When I load name foo, it gives me an object called function. So everything is just a dictionary or table lookup. And that table happens to be the global table because, let me switch back to this picture here. Let's see, we're here, well, before we call foo, that one. So this is the table. Inside of the Python interpreter, there's a table that says global frame x points to 10, foo points to this thing, bar points to this thing. Good. So in Python, no one prevents you from doing something silly like this. This is actually a great example they brought up. That let's say I don't know, I made it backwards, okay, like that. So don't do this, but I just said call x a foo. This is the exact same code, except I just switched it, right? I made a typo. I switched it. I thought x is the function and foo is the calling it, right? So the opcode here, the opcode is just load x, load foo, call function. It still compiles. It's perfectly fine code. But when you try to run it, they'll give you an error. And it'll give you an error because when you try to call function, it'll say x is not a function. You can't call it. So let's see if it actually works. So in Python, everything is at runtime. There's nobody prevents you from writing this code. The only code you can't write is code that doesn't parse. So if I say, all right, not callable. All right, so this what says is that you're trying to call a function call on an integer and it's not callable. It's not a function.
For the call function, like, so when you're executing the bytecode, do you kind of like the opcode is run one by one, right?
Uh-huh.
And when you run the call function, do you kind of switch into the function and then run that one by one and then come back, or so all that? But in the old code, how do you see that operation? Isn't it just one by one?
Yep. Good question. That's what we're going to go into in the interpreter. Man, you're really good at predicting stuff. This is great. This is good. This is really good.
Okay.
Right. So the question was, how does that actually work in the interpreter? So before I get into that, there's one more missing piece, though. The missing piece is that I never actually showed you what the code is in foo and bar, right? This doesn't actually show you that. This just shows you, this is not satisfying because it just shows you the code here. It doesn't go inside, right? And the reason why is because when the default mode of the disassembly only shows the outside. To actually get to the inside, you can write this down as a note for, so everyone just sees this code. The most important thing to remember about this is the call function call, which we'll go into in detail in the bytecode, like your question. But to actually see what's inside, I have to go into Python. So I'm going to clear this. So we're going to go into Python itself. So type Python so we can see the three things. So now what we're going to do is we're going to import dis, which is the disassembly module, inside of Python. This allows you to access the assembler. And then what we're going to do is we're going to do import test. I had a typo, sorry. Let me undo my typo. Import test. So what import does in Python is that actually loads the whole module into Python, executes it all, and just executes it all, and loads it all in. So now test is actually a module in Python. So I can actually say test.foo, test.bar. Those are both functions. You can access them as functions. So I'm going to clear the screen again. Now if I do dis.dis of test.foo, this gives me the code for the foo function in test. And dis.dis of test.bar gives me the code for the bar function. So I'll wait for a second until people get to that. That disassembles the individual parts inside. So again, you have to actually go inside the Python interpreter, import test, which is your file, and then go individually into the things. And these, so actually let's look at this code here. I'm gonna go around and see if people are able to get this command, because I want to get some speed on this. Okay, does anyone need help getting into this code? Okay, to seeing this output. Okay, because I can just go around and see this output. Okay, so again, I'm just going to read over the opcode again. It's pretty straightforward again because foo and bar are small functions. Now the foo code is here. Lines 4 and 5. Line 4 is here. Line 5 is here. I'm just reading off the lines. Bar is line 8 is here. Line 9 is here. Make sense? The line numbers are all relative to this thing, so you can count off 1, 2, 3, 4. Okay, so foo line. This line is we load something. It's called load fast, which is a special opcode. Again, you can look this up for a local variable. We load x in a fast way because it's local. Load constant 2. Multiply them and store them in y. That's exactly this line. X times 2 store in y. The second one here is load global, another opcode. It tries to find a global variable named bar, because bar is a global variable somewhere. If it finds it, it loads fast y, which is this thing, calls the function, and then returns whatever the function returned. So that's that. Bar is very similar. Load x, load const, divide, store, load, return. So all these should be straightforward, right? Load constant, divide, store in y, load y, return. All right? It's all just pretty boring, straightforward stuff. So the only non-boring part here is again that foo does a call function in itself. So if you're really curious, as a shortcut, if you just say dis.dis test, it will actually disassemble both the functions inside. It's a convenience. Yes?
So is it possible to optimize this bytecode, like inline the bar function into the foo function?
Good. So is it possible to inline the bar function and call function? Yes. So a great project would be to do some optimization on this. So I think I mentioned last time that you can write down a note. For your project, there is a library called byteplay, B-Y-T-E-P-L-A-Y. It works on Python 2, which is the version of Python we're doing. And it's a Python-based interface for playing with bytecode. So you can actually import your bytecode to byteplay, tear it apart, inline stuff, move it apart. That's actually a really great idea for a project. So Python itself does not do any real optimization. That's why it's actually easy to study, if you notice, because the bytecode is very unoptimized. There's some called peephole optimizations, very small ones it does, but for the most part it doesn't optimize. And notice the dis module isn't very advanced. It just prints it out, right? So if you want to really do optimizations, this byteplay library is great. Okay, so we're going to spend the rest of the time tracing our way through the code, just kind of searing this into your memory. I'm going to be a bit more abstract when tracing through the interpreter because it will be very tedious to trace exactly these steps, especially live in class. So we're going to do a little bit, think a little bit more abstractly when we're going through the interpreter. So recall this is the main interpreter loop. we have all the bytecodes and stuff. So let's focus on the call function bytecode. Actually, before that, let's look at frames. So one of the hard things about starting up in this class is that there's a lot of code to look through. I mean, we're going to reuse the same code again, so we'll give you multiple exposures, so don't worry about the first time. So do include, go look at include, and look at open code.h, code.h, and include. So it should be under Python, include with a capital I, and then code.h. And then also open up frameObject.h, also an include. So there's two H files, code and frameObject. Okay. So very quickly, what the code.h is, this is a bytecode object. This is the code object in Python. It has a lot of fields in it. We won't need to know a lot of them, but some of what the code object contains is co_code. Remember, this is what we accessed from last class. Like, we did something .co_code. This is the actual bytecode. This is just a raw string or list of bytecodes. This is the actual code. But that's not enough, because we want to know some other information about it. We want to know what the names are, so we could refer to stuff by pretty names instead of just a position in the bytecode or something. So there's variable names, there's some of these other things. There's the name of the function, there's a file name. So I think, though, your question about tracing through the thing with GDB, you can actually look at the code object and look at the file name. So I think if you break on co file name equals test.py, you should break on the file name. This is for debugging. Arg count is how many arguments this function took. So remember, foo and bar both took one function. So the code for this should actually take one arg count 1. And locals is how many local variables are there? 1, 2, 3, so forth. Stack size is another thing. So basically what the code object gives you is just information about this piece of code. Now notice the one thing that this doesn't give you is, well, it does give you a name, but so I think you can't use it. But you can, that name doesn't have to be unique, right? It's just for debugging. So you can assign this piece of code to something else as well. And code objects are supposed to be immutable. So once you create one, you can create a lot of sharing to it. The second concept is a frame object, and this is going to get to the heart of today's class, which is, you can ignore all this above. So this object, it's kind of big, PyFrame object in frameObject.h. It's called PyFrame object. The most important thing here is here, F code, built-in global local value stack. Okay, so this is to answer your mysterious question of how are these represented in memory. So in C, there is a stack of frame objects, as well as a stack of a value stack. So this frame object is implemented as a stack, and it's actually implemented as a linked list. So if you notice how this actually gives a pointer to itself, an F back pointer. So there should be a, I don't know, there's a frame stack somewhere, and every function call, there should be one. So this is global, and then this is foo, and then this is bar, and then these link back to each other with the F back field. That makes sense? So it actually creates a linked list of frames. And this happens when we execute. So I'm gonna, it's gonna be messy, but I'm gonna put up Internet Explorer, and well, you should remember the picture from above, right? When we were executing, there was the frames, global, foo, and bar. Each one of those inside is a frame object. And the frame object contains a pointer to the last frame object to make a list, F code, which is the code that is executing for this frame, right? The code that is actually executing. It contains a pointer to some other things like the globals dictionary, the locals, the built-in. The globals is very important. That's like what global variables you can access. That's your question about the global table. That's the global table for this frame. So every frame can have a different global table, because if you're executing a function somewhere else, their globals might be different than your globals. So the frame is the winner there. The frame dictates where you find your own globals. For most code, all the globals point to some global. There's a value stack. So notice how this is actually the value stack. So the value stack is in the frame. It's in each frame has a value stack. So you can imagine each frame itself has a stack inside. Has a little stack of things. That's its own private value stack that's using for the computations. And the hope is that when you get out of the frame, it actually clears the value stack. So it clears everything up. So when you exit this frame, all the Python interpreter does, it cleans up all that and cleans up all that. Because otherwise, if you don't clean it up, you're going to have memory leaks in places. So these are all other things. Value stack, locals plus value stack. So the actual thing that you'll actually see, this is kind of a tricky variable name, f locals plus whatever. What this actually is that technically what happens in a frame is that I'm just going to do a frame for foo. So foo is here. Technically, as an optimization, the local variables in the value stack are stored in the same list. So actually there is a f locals plus here is actually a bunch of local variables followed by the value stack. It's just an optimization so that, but conceptually there's two things. There's a set of local variables for every function, because you need to know where the local variables are. And then there's the value stack for the opcodes to operate on. But it's all the same one jumbled thing. So it might be confusing when you see this locals plus, but conceptually there are two things. There's local variables, there's a value stack. It just stores in one structure. It knows how big this is at compilation time because it knows when it compiles a piece of code how many local variables it has and how many arguments it has. Because the code, if it sees, oh, we use 5 local variables, then it makes a array with 5 things. And the value stack could be arbitrarily big. It's actually a fixed size, but it could grow. So that's a frame. Again, we'll go back again over this again and again, but this is the basic structure of a frame. So in the last 10-15 minutes or so, I want to actually go over the execution. So now that you know what a frame is, let's actually go back to 690, the start of this function, this pyexec thing. So we're going to circle back again, and hopefully by repetition we'll get this a bit better. So now we should actually be able to see what this thing does. It takes as an argument a frame object, a pointer to a frame object. So what this function does, this main interpreter, is it executes a frame object. The frame object inside has code. It also has pointers to globals and other environment state. And all this function does is execute the frame, get out of there, and return the return value to whoever called you. All right, so this is executing one frame. And again, there's a lot of there's potential confusion because there's several related terms. There's frame, there's function, and then there's code. All right, there's 3 things that seem like it's really confusing in your head now because there's 3 things that are almost the same, but they're not really. So I'll clear this up. A code object is the most primitive thing. It's a bunch of bytecode. Actually, there's a 4th thing. So there's bytecode also. A code object contains a bunch of bytecode. Bytecode is just a string of 1s and 0s. A code object has bytecode. It also has some extra semantic information like constants, variable names, some nice wrapping. A function has a code object, and it also has an environment. It also has an environment pointer to where it was defined. And a frame, confusingly enough, also has a code object and also has its environment. So a frame is the representation of code at runtime when you're running it. A function is just a static thing that is at compile time. So it's a little confusing. We'll make it more clear later on. But yeah.
So frame and function are different because of what? They both have code and environment, but they're different.
Yeah, they're different how. So a frame is A function, as you can imagine, is a kind of object that you can expose in your code, and you associate variables with that function. A frame, you don't access the frame directly. A frame is just a runtime representation of code, but they do share the same data, right? So you can say a frame is okay. Here's a good way to clear it up.
I thought it's just a function is just a specific instance of some kind of frame.
You can say the other way around. So actually, let's
Frame, okay.
yeah. So let's actually clear this up. This is a good question. It was here. I'm going to write a recursive function. Factorial n if n is less than or equal to 1, n else. This is a standard factorial function. I don't have a bug. X equals factorial 3. So unless I have a really bad bug, let's try this. Okay, good. So for those of you who haven't seen, this is a standard recursive function that calls itself. It keeps on calling itself, right? Factorial will call itself until it gets down to the base case. So notice here, there are actually a lot of frames. Frame, 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 frame. There's only one function. Make sense? There's one function, there's 4 frames. Because each frame is a runtime representation with its own local variables. A function is just...
A function, okay.
Yeah, does that clear it up? So that's actually, this illustration clears it really well. There could be multiple frames for the same function. And each frame is unique, because this one is 4, 3, 2, 1. But there's only one function here. So when we're running, we're all talking about frames. So actually, you can even forget that functions exist for now. Okay, so this evaluates a frame. Now all the boring opcode stuff we can skip because we did this last time. The only opcode we really care about is call function right now. Okay. Just killed it. Okay. Sorry. Call function. Seems deceivingly simple, but we're gonna look into this in detail. So recall the call function opcode. We push the function name on the stack, and then the argument names, and then we call a call function, and then we return the value. Magically, what happens? So when you see a call function opcode, first it you can avoid this TSC thing. It calls call function. It calls a C function called call function, and then it pushes. It returns some object. It pushes it on the stack, and then we're done. So what a call function opcode does is call the function, and then leave the return value on the stack, and then we're done. Because the next opcode should probably grab it off the stack and do something. Okay, so now we're going to spend the rest of the classes diving into this, what this call function does. So we're going to enter this function called call function, not surprisingly. This line is on 3992, so you have to go down quite a bit. The call function is 3992, so go all the way down. Oh, another thing is it'd be useful if you have a text editor with not line numbers. Otherwise, it's really hard to find. So I use Sublime Text. I am not trying to advertise anything particular. This is free, so if you go to Sublime Text on Google or whatever, Sublime Text you can download for free on Windows and Mac and use it. And it has line numbers. So Sublime Text, for those of you who are using an editor without line numbers, that's just an easy one. 392, it's call function. What this actually does is a bunch of cruft right in the beginning, because if you actually look at the call function bytecode definition, sorry, I'm gonna go here. Call function. Okay, so what does it say? Calls a function, the low byte of argc indicates the number of positional parameters, blah, blah, blah. Don't worry about all the rest. Basically what this says is that the argument that you pass to call function tells you how many parameters you're going to pass into it. It doesn't actually tell you the value of them. And then based on how many parameters, it will actually look up the stack to find them. So if you want to call a function with 3 parameters, you need to push 3 things on the stack and then the function, 3 things on the stack, then the function name. So then when call function knows that there's 3 things, it pops 3 things off the stack and then use all of them as parameters. So what this boring code does is it actually grabs the number of parameters on the stack. It's just some pre-processing. And then it checks to see if it's a C function. So Python, there's 2 kinds of functions. There's actual functions written in Python, and there's what's called C functions. C functions are functions written in C code. They're usually optimized functions. So you won't read any of those, but in the library, standard library, there's a bunch of them. So this fails this check. We're going to go all the way down to it. There's a lot of different kinds of functions, but basically we're going to do this one right here, 4053. Py function check means, are you actually a regular function, like not a fancy weird function, just a regular Python function, and it's yes for us. And if it's the case, we're just going to call fast function, which again dives you into a whole other thing. We're going to call that with a bunch of information about our parameters. So fast function is 4083. So we're going to go down more. 4083. Again, if you can't follow along now, just write down the line numbers so you can follow along. 4083. Fast function is what this takes in is the some object that represents the function you want to call, some object that represents the current stack, and it basically 4083, 4108. So the first thing that it does is 4108 py frame new. This creates a new frame. So this is getting back to your question. When you call a function in the C code, it creates a new frame out of magic, out of thin air, and assigns it to F. This new frame, if you notice, how is this frame created? It's created with the code, CO, and the globals. This is exactly the code that the function had. Where's code? This is the code of the function you want to call, and the globals, the pointer to the globals of the scope. So now this frame knows that I have a global and I have some code to execute.
And the global is going to be the same as the parent who creates the
That's right. That's right. That's right. It's the globals pointer of the function itself. Yeah. There's a lot of bookkeeping code you don't need to worry about. I know, the danger of studying real code is there's a lot of extra stuff. And then magically, lo and behold, actually, let's do one more thing. So it creates a new frame, and then it does this thing here. What this thing does is it actually copies the arguments from the stack into the new frame. So f locals plus, remember f is our new frame? F locals plus is that storage for local variables and the value stack. This is our existing stack, our old stack from our calling function. N is the number of arguments, I'm assuming. And this increments what it does, this piece of tight loop, what it does is it just copies the arguments from one frame to the other. So I'm going to draw examples. Remember, foo had the frame for foo had inside. I don't remember the values. It had x is 10, y is 20, and then the bar is actually. Let me just draw it on my other drawing. So I'm going to go. So what this code does is it implements the passing by value semantics. It passes the parameters. When you're calling a function, you need to pass the parameter somehow. What this does is that it passes the parameters. Now let's see if my paste actually works. No, it doesn't. Let me go here. Thank you for pointing out the copy. Okay, so what this piece of code I just said does is the following. Okay, so we're here. Let's just start simpler. We're here. We're going to call a function foo. There. The code we just went over did is it creates a new frame object. It didn't. That frame object. What it has inside is it has the code to foo because it knows foo is executing. It has a pointer to the globals. But the code we just did is we actually made a copy of this x10 to this x10. Right, we made a copy. It needs to copy it because foo of x here needs to go into this thing. And similarly, when we go to bar, it needs to make a copy of actually these two, right? The y20 needs to be copied to x20 because this one goes into this one. So all that does is just implement copying of the parameters. Like you have to copy the parameters, right? Otherwise, how do you pass stuff from function to function? So it copies it here. You can look into this code in more detail itself. Basically copies it. And the last magic thing before we go is it calls our function. It calls that pi eval frame x, that giant function we were studying yesterday. It just straight up calls it. And what does it call it on? It calls it on the new frame we just created. We created a new frame, f frame new. F is pi frame new. Now it just says, hey, we set you up. We gave you all the parameter values. Go and execute. When you're done executing, what do? We assign your return value to this. We assign the return value, and then we're going to get out. Hopefully we get out of here alive. Return value, return value. We get out. Good, we pop out of the stack. Now we're on 4054. So now we remember who called us. Again, the interpreter does all automatically, 4054. We were called with this fast function. We got the return value, we got x, good. And then it does some cleanup code. It does some actually this clears the stack. So this is your question or someone's question about clear the function stack. After you exit a function, it just kills the stack. Just like, yeah, we don't need it anymore. The frame is gone. Return again to the caller, and then 2681. So this returns the value of the caller, and then we're going to go up to just where we came from, and then we'll get right out of here, 2680. Remember the whole thing, this whole adventure started with this call function opcode, right? We got into here, we assigned to x. Now we're going to push x onto the stack, and then we're done. So let me just show you, recall one more time what happens here, and then we'll get out of here. That is all this magic right here, right? We loaded the function, we loaded the thing, we called it. After we called it, it left the return value on the stack. And then the store name, z, took the return value of this thing and threw it into z. And then we're done. So that's the function call right there.